Okay, so I had a hard time finding resources and documentation on how to implement a frequency domain pitch shifting algorithm on a DSP. But then I finally came across uh, this research paper on how to actually implement it on a DSP. But I was still having trouble implementing it because it didn't really have like example DSP code. But then luckily I stumbled across source code from one of the people who wrote the actual research paper. This guy, Nicolas Jurat. Okay, he has the same first name as me, so that's pretty cool. So I used this source code, kind of just, it was in Java, converted it to C, and I'm like, well, I hope it kind of works on the DSP. Sure enough, it did. After some tweaking, had to change some stuff, but I'll talk about that in a little bit. So I have this on my GitHub already, and first I'm going to demonstrate it so you can see how it works, see how it sounds. Now it's not going to sound perfect because I'm using the same microphone that I'm speaking to right now to also hear the effects of the pitch shifts. Um, but anyways, I promise you, it sounds pretty good. Okay, and it's like really low latency. So I'm gonna show you how it sounds, and then we'll go over the code, and I'll tell you what you need to keep if you're implementing this on another DSP, and what you need to change, etc., etc. So right now the pitch shift ratio is set to 1.3, so it's gonna sound like a higher pitch voice. So I'm gonna play it, and then I'm gonna whisper into this mic because if I speak too loud, you're gonna be hearing both, right? So.
Testing 1 2 3. Testing 1 2 3.
So that's with 1.3. Now I'm gonna go lower. I'm gonna go to like 0.75.
Hello, testing 1 2 3. Testing 1 2 3.
So as you can see, the audio is still intelligible, so it preserves the performance and speech pretty well. That's one of the benefits of the frequency domain approach. And it's in pretty real time. I mean, it doesn't get any more real time than that. If you want to get faster than that, you have to implement Roller's algorithm, which uses an FPGA to parallelize the whole problem, and it goes really fast, whatever. This is on a DSP, less than 20 milliseconds latency. At least that's what the paper suggests. Pretty damn good for a DSP, right? Only using one CPU, no fancy crap, just boom. Regular algorithm. I guess there is some fancy stuff because it has to do a FFT and an IFFT. So let's actually go through that code. So I'm gonna start from the top. So the first thing is I just include all these libraries and stuff. This is just for the DSP, specifically for this TI DSP, this F28 project. This stuff is for just basic C libraries. This library is a library I made to interface with my I2C LCD driver. You don't have to worry about that. This is also for a TI. This is also another TI library, TI library, TI library, my library. Also TI library, right. So really, I mean, the only thing you would keep is this, and then maybe whatever other libraries you need to interface with some other hardware you're using. So I create the structure because I have to deal with complex numbers because we're working with FFTs and IFFTs. So it deals with complex numbers. So I created a simple structure to just store a real and imaginary number in one data type. I'm doing a reverb effect, which I'm gonna gloss over this because it's not relevant. I'll show you the reverb effect right now. Just, okay.
Hello, this is no reverb effect.
Hello. This is with reverb. So it sounds like communicating. A little less intelligible, but I did anyways. Okay, I'm gonna have to go right now for a second. I'll be back. Okay, where was I? So yeah, disregard the whole reverb stuff. That's not necessary. The whole IIR bandpass filter. So this is actually important. So this is where we actually start the ocean pitch shifting algorithm. So I ran out of memory on my DSP, so I couldn't do a bigger block size. But with bigger block sizes, it basically uses more data or audio chunks to perform the pitch shift, which I guess makes it better. But I could only do up to 1024. Overlap and zero pad, I found 4 and 2 to work best for me. Then everything else is calculated based off those values. This is pretty much the same. This is just off the formulas. You don't have to worry about this whole data section. Whenever I do pragma data section, this is just for this TI DSP, just to make it such that the data types for the FFT, they're aligned within certain memory boundaries. Don't have to really worry about that. But yeah, this is what I'm using also in the actual pitch shifting. So you have to take an analysis window of a certain size, and then that's where you perform the FFT on. And then you recreate the signal by doing the IFFT of the pitch shifted result. That's the synthesis window, and they're both the same size. Unity roots, you do this in the beginning to calculate. You just generate the unity roots in your main loop before you go into your main loop, and then it uses those over and over again as part of the algorithm. And then yeah, you just have more defines. So this is for the TI FFT. It's RFFT because it's a real FFT. You're doing it on real data. Doing 10 stages, so that's 2 to the 10. So 1024 samples. This is the same as my block size. So if you're on a different DSP, you would have to implement the FFT some other way. Usually, like if you're using like a DSP from ST, they should have their own FFT library and IFFT library to deal with that, like I'm doing. And then likewise for the inverse FFT, it's a CFFT because it's creating a complex, or you're using complex results from the FFT to create the real output. Same stages as the real FFT. Except now the input buffer is ×2 because you have a real and imaginary data type for each sample. But you don't have to worry about those details so much. Just know that if you're on a different DSP, you need to implement your own version of a FFT or IFFT, either by writing your own function or preferably using some library from your DSP company that you're using. So it has some booleans here that I'm using to kind of control how I'm doing this. So the way I'm doing this is using a MIC DSP register. So I talk into the mic, records data, fills up a buffer. When that buffer is ready, I say, okay, now it's ready to process. Process the data. When it's done processing, it says, okay, now it's ready to play. And then it sends it on the MIC BSP transmit. And then it sends it to my audio codec, which then is already connected to the headphone out. And then it plays the pitch shifted result. So I'm going to skip this stuff. These are just function definitions for my whole file, for my main file. But in terms of the pitch shifting functions, basically it's these. Yeah, only these functions are used for the actual pitch shifting implementation. So the other functions, this is for reverb stuff, which you don't need again, and this is for the bandpass filter, which you also don't need, but it makes it sound nice, or it cleans up the audio, so I would recommend it. Yeah, definitely don't need this. So this is also something that's specific to my DSP. I have some other ISRs that I'm using because I have my rotary encoder to switch between pitch shifting ratios, and it has attached on it a push button to implement the reverb effect, so you don't have to worry about these. You just have to figure out your own way of taking audio in. In my case, I'm using the MIC DSP protocol on my DSP. I know ST also has a MIC DSP protocol as well, so I'm sure you'll do something similar. This is just initialization stuff for this device. This is for reverb. You don't have to worry about this. This is something you have to do for the pitch shift implementation, so you have to make sure you initialize this. You don't have to worry about this. You do have to do this. This creates a handing window that basically smooths out the input. It kind of looks like a bell-shaped curve kind of thing. You have to do this fill array and generate unity roots. And this is where I actually set up the FFT and IFFT pointers so it can start computing and stuff. This is specific to my DSP, this codec initialization stuff. This is just to make sure that the mic data is being used as the input to the codec, and I set a sampling rate of 32 kilohertz. That's all. Some ISR stuff, which again, you may use for the MIC BSP receive if you're using the MIC BSP protocol. The other interrupts are just for general purpose input output pins that is used for the rotary encoder. And then more ISR stuff for the pi vector table for interrupts to fire and all that crap. So I don't have to worry about that. All right, so main while loop. So the way this works is when there's data ready to process, which is determined from an ISR, then it processes the data, right? Makes sense. So this is how we actually perform the pitch shifting. This actually does the pitch shifting here. So before we do that, though, I clean up the input by applying a passband filter, IR filter, gets rid of unwanted noise, and then I process the data on that. And sometimes artifacts are created when you do that. So before I send it to audio out, which actually gets played to the speaker, I do another IR filter, the same coefficients, just to clean it up again. I have two versions because either I'm doing a reverb or I'm not. But again, if you're not doing that, you just do one IR filter on the sound data that's being updated by process data. So this takes in a pointer, so it modifies the data here. It doesn't return what the pitch shifted array is. It just modifies the actual array. That's how I chose to do it. You don't have to worry about this. This is just for the LCD stuff. All you have to really worry about is implementing something like this, and then it'll work fine. So how does it actually do it? So process data, this is actually doing it. So you can just read through the comments, how it's working by reading the research paper. And I'm also going to link in the GitHub, I'm going to create a README that will also have the actual source code I used to create this, so you can see for yourself how it works. But two important things to notice here. So this RFFT F32, this is an assembly code written by TI to actually compute the FFT. Do a bunch of complicated stuff. Won't go over that. I don't know how it works personally. So you're gonna have to replace this with your own FFT implementation. This is something else that you need to take into consideration as well, because for fixing the input spectrum, because the algorithm is expecting the data to be of a certain format. And depending on how you implement your FFT, you need to format it a certain way. So let me go to that to show you what it means. So basically, and I kind of wrote it here in comments. So the algorithm assumes FFT is taken over 0 to n minus 1, where n equals block size. So my output of the FFT, the TI output of FFT, what it does is it does for 0 to n over 2, so half the block size, from 0 to half the block size, it has the real values for n over up to n over 2. And then from n over 2 to plus 1, n over 2 plus 1, all the way to n minus 1, it has the imaginary values. But they do it weird in the sense that the last value of the output buffer of the FFT is the imaginary version of the first index, not of the, so really the second element. So it's kind of confusing how they did it. So, but if you look at it, you'll see what I mean. This is how they did it. So depending on your FFT implementation, it may be different. So you have to take into consideration how your FFT outputs it. Sometimes it may alternate. It might do real of 0, imaginary of 1, real of 1, imaginary of 2. In my case, it just does it like this. Likewise for fixed output spectrum, it depends on how your inverse Fourier transform is expecting the data to be input. The way mine was expected to be input is alternating real, imaginary, real, imaginary, real, imaginary. That's why it's 2 times the block size, because you have a real and imaginary value for each sample of n samples. So it's 2n samples. Yeah, you can read over that to see how I solved that. It was pretty simple. It wasn't too big of a deal. So yeah, back to where we were. So we fixed the input spectrum. And then process spectrum, this actually does the pitch shifting algorithm. So we can go to that process spectrum. So this is the actual, algorithm itself. This is the meat and potatoes of the research paper. Basically what he was trying to figure out. This kind of does all that stuff. And yeah, and then we fix the output spectrum, because once we have that shifted, now we need to reconstruct what kind of real signal would have created that pitch shift. So then that's the whole point of the IFFT, the inverse, is we recreate some signal or synthesize some signal to reproduce that pitch shifted result. So that's what that does. And you apply the synthesis window to clean it up. You do some overlap add stuff. I'm not too sure on why you need this stuff, but it kind of need it. And yeah, increment counters, and Bob's your uncle, right? So yeah, that's pretty much it. It is kind of complicated. Definitely wasn't as simple as I thought. I tried doing some simpler things in MATLAB, and it sounded weird. Like, it was pitch shifting it, but it was not preserving the formants at all, and it just sounded intelligible. So I guess it needs to be this complicated for it to sound proper. So yeah, I'm gonna update my GitHub soon to include the README with some other information. But yeah, hopefully it works for you. Yeah, see ya.